Salutations, many mathematicians. We're getting into scientific notation. So our purpose today is to be able to write numbers in scientific notation and identify if a value is written in scientific notation and be able to list from least to greatest. So sometimes we call scientific notation sino. So you might see me write that like sino, just so I don't have to write out the whole long word. It's an abbreviation. So scientific notation is a way that we can write really, really big numbers or really, really small numbers. For example, if I use my calculator, and we all know 2 raised to the third power is 8. What if I raise 2 to a power that's so large, it doesn't fit in my calculator anymore? And that's where scientific notation comes in handy. Notice it puts it as 1.152921505 times 10 to the 18th power. So we are in the decimal system, which means everything is base 10. A long time ago, we used to be in a different base system. We've evolved many hundreds of years. We've evolved, and we've used a decimal system for a long time now. But a long time ago, we used a base 60 system. It was a sexagesimal system, and that's why time, 60 seconds in a minute, 60 minutes in an hour, is still base 60. So we still have that from a long time ago in math, was base 60, everything. So taking a look here, since we're base 10, scientific notation has to do with multiplying numbers by a power of 10. So notice this is times 10 to the 18th power. So we're going to look a little bit more into scientific notation today. So taking a look, most of us would agree that texting is a fast and efficient way of communicating. In fact, texting allows us to abbreviate many common phrases. LOL, laugh out loud, 143, I love you, right? 143, I love you. It was a really popular song when I was your age, okay? Mathematics and scientists have a way of expressing really large and really small numbers in a fast and efficient way, and it's called scientific notation. Just like texting allows you to communicate quickly, scientific notation allows you to write really small and really big numbers more efficiently. So we're going to take a look at these 4 expressions below in standard form. So when we write something in standard form, that's like the decimal expansion. It's the number if we wrote it out. So if we take a look at 500,000 times 10 to the negative first, well, we learned last time about negative exponents that 10 to the negative first is really 1 over 10. So I am losing 1 decimal place, or think about dividing this value by 10. So I get 50,000. 50K, nice. Here, I'm multiplying by a value of 10, 1 power of 10, and so that means I move the decimal over once to the right. And again, I get 50,000. The next one, it's 5 times 10 to the 4th. So we're multiplying by a power of 10 since we're in the decimal system. Each decimal place is a different value of 10. I'm multiplying 5 times 10 to the 4th. This is going to be 5, and I'm going to add 4 zeros to represent the 4 decimal places. 1, 2, 3, 4. Again, 50,000. And the last one we're going to look at is 0.5 times 10 to the 5th. And so that is 0.5, 5 tenths times 10 to the 5th. So we're going to move the decimal place over 5 times to the right. And since there's already 1 decimal place spoken for, that's only adding 4 zeros. Wow, 50,000 again. So notice in the above problem, only the expression 5 times 10 to the 4th is written in scientific notation. And that was one of our goals today, our learning outcomes, is can you tell when a number is written in scientific notation? So any number is written in scientific notation must be written in a special form. So this form is A times 10 to the n power. And n is called, well, n is that power of 10. It's going to determine how big, if it's positive, or how small, if it's negative, this number actually is in standard form, what the value is. So this n, thinking about other things that we talk about how large something is, an earthquake, right? What's the magnitude of an earthquake? So n is called the magnitude and must be an integer. So remember, integers are positive and negative whole numbers, including 0. So no fractions, no decimals here, but can be positive or negative. And 10 to the n we call the order of magnitude. Okay. And something else we need to look at is we need to look at this a value. So a is called the significant figure. Kind of like your significant other. We love our a. Okay, so a is called the significant figure. I can't help myself. I'm going to have to put a little heart. Oh, significant figure. And a has to be greater than or equal to 1, but less than 10. So greater than or equal to 1 and less than 10. So a cannot be 10, but a could be 9.9. A could be 9.058321, right? A can be 1, but a has to be less than 10. It cannot be equal to 10. Okay, so what we're going to do is we're going to do a little bit of practice. I'm going to give you value in scientific notation. You're going to give me that value in standard notation, or I might give you the value in standard notation. You're going to give me that value in scientific notation. So I'm going to take you back to when I learned this back in the day, and my teacher taught it to me this way. Okay, so here's the number times 10 to the 8th power. So that means this exponent tells me it's positive, so we're moving to the right. So we're going to take 6.345 and we're going to move the decimal point to the right 8 times. 1, count with me now, 2, 3, 4, 5, 6, 7, 8. Now put in zeros for your placeholders. Count backwards to put in your commas. 1, 2, 3, comma, 1, 2, 3, comma, 1, 2, 3. Cool. I have to tell you, I sometimes went loop-de with all those loop-de's. I would miscount. Just things wouldn't happen. But what we can also think about is that you can show all those loop-de's if you want to. But here we can think, well, we're moving 8 decimal places to the right. I already have 3 decimal places. So I just need 5 more, and those can be zeros. 1, 2, 3, 4, 5. And then to communicate clearly, of course, count backwards for our commas. So we can say this appropriately. This would be hundreds, thousands, millions. So 634,500,000. Awesome. Great job writing it in standard notation. Looking at the next one, 8 and 400ths times 10 to the 4th. Well, we need to go 4 decimal places to the right because the exponent times 10 to the 4th, we're getting bigger. There's 2 already there, so we just need 2 more zeros. Count backwards for your commas, 80,400. On the other side here, going from standard notation, well, remember this a value has to be greater than or equal to 1 and less than 10. So for here, that would be 5.32. We don't have to put the 0 there, but we do need to include all the other digits in our significant figure. Times 10 to the, to go back to our original number, we need to multiply and get bigger to the right. And that's 1, 2, 3 decimal places, so it's times 10 to the 3rd. And you can always double check that. You can always grab a calculator and double check it if you wanted to. So if I grabbed a calculator, I could put in 5.32 times, and I'll just put 10 raised to the 3rd power, and I get 5,320. Yay! Okay, so the next one we would write, remember we want it to be 4.2 times 10. There's 3 zeros and 2 more, so 10 to the 5th power. So let's look at a number that's getting really big or really small. and that's going to deal with negative exponents. So if we jump down to 8.12 or 8 and 1200ths times 10 to the negative 7, we are going to have a number that's smaller because the exponent's negative. We're moving the decimal place to the left, and we're moving the decimal place 7 times to the left. 1 decimal place is already accounted for, so not including the 1, the 0 in the ones place, because that's not a decimal place, you guys. That's the ones place, right? But we're only talking about decimal places here on the right side of decimal point. That's going to be 6 more. So 6 more zeros, 1, 2, 3, 4, 5, 6, and then put 8, 1, 2. All the numbers that are there. You can always count by going back 1, 2, 3, 4, 5, 6, 7, and notice we would end up at 8.12. So the loop-de's are helpful, but don't depend on them. Over here, notice if we wanted to put our decimal place to have a significant figure greater than or equal to 1 and less than 10, we want our decimal place here. So this is going to be 4.005 times 10 to the, we want to go back to this original number. So it's going to be a negative exponent because we're getting smaller than our significant value, significant figure. And so it is 3 decimal places, so -3. And always double check to make sure that you are correct. Okay, go ahead and finish this table, and we will finish the page as soon as you're ready. Okay, let's see how we did. Okay, so we have, where did we leave off? 4.26 times 10 to the 5th, we're going to end up with 426,000. 3.2 times 10 to the negative 3rd. This is the 10th, hundredths, thousandths, 10,000, so that's 32 10,000ths. And then the next one, I'm not going to try saying it right now, but 1, 2, 3, 4, 5, 6, 7 zeros, and then 42. So let's see. Okay, I have to say it now. It's like a dare. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, billions, 42 billionths, I think, possibly. And the last one we did already. Here, the last one we left off on was 100,000 millions. 9 billion, 40 million is 9.04 times 10 to the 9th. See how more efficient it is to just say this in scientific notation than counting over and thinking all those place values? Cool. The next one, 5.4 times 10 to the negative 6. And the last one you had to do 7.5 times 10 to the negative 4. So much more efficient to communicate with sign-out. So fill in the blank in scientific notation. If the exponent is positive, the standard decimal number is moved to the right. In scientific notation, if the exponent is negative, the standard number's decimal is moved to the left. To the left, to the left. Everything that's less goes to the left because it's getting smaller. Okay, so let's take a look at some applications of scientific notation. So why don't you finish 4 and 5, and we'll see how you do. Awesome. Number 4, we are writing this number in scientific notation, hundreds, thousands, millions, billions, 500 billion. It's just 5 times 10 to the 11th power. And the diameter of human hair, I mean, I have a lot of hair. Maybe we could add up all the diameters of my hair later. That'd be a fun problem. Taking a look here, obviously we're going to have a negative exponent. This is 9.9 times 10 to the negative 5th. Remember, your significant figure needs to be greater than or equal to 1 and less than 10. Times, we always use an X for the times. You have to use the X for times in scientific notation, or it is not in scientific notation. Cool. So explain in words why 27.5 or 27 and 5/10 times 10 to the negative 3rd is not written in scientific notation, and then we're going to write it correctly in scientific notation. So the explanation, well, something about this is fishy. It doesn't match our definition. Remember what our definition is. Our definition is a times 10 to the n, where n is an integer and a is greater than or equal to 1 and less than 10. Less than 10, oh, That's the issue here. So explanation, the significant figure, significant figure, and please use the correct math academic vocabulary here. The significant figure is too large. 27.5 is greater than 10. Perfect. So written correctly, these are the steps we're going to take, and this is a really important skill for the rest of the module. What is the issue with this? Well, the issue is 27.5. So we're not changing the value of this expression. It's still going to be 27.5 times 10 to the negative third. But what we are going to change is that it needs to be written in scientific notation. So we're going to focus on that 27.5. So we want it to be 2.75. 27.5 is 2.75 times 10 to the first. Times 10 to the negative third is still here. Now we're going to use our exponent properties. So since we're multiplying with the same base, what do you do with your exponents? That's right, add them. So our final answer, written in scientific notation, is 2 7/75 or 2.75 times, using an x for that multiplication, 10 to the negative 3 plus 1 is negative 2. And that is your final answer. And this is a skill that's going to be really important when we start to add and subtract scientific notation. Okay, so number 7 says, examine the numbers below. If the number is written in scientific notation, circle it. If it's not written in scientific notation, rewrite in Sino. So I'm going to do A and B with you. Okay, let's look at A. It's not written in scientific notation. Oh no, that significant figure is too big. So we're going to focus on that 348, and we're going to say, well, if it was written in scientific notation, just 348 would be 3.48 times 10 to the second. Bring down times 10 to the eighth, and then think, oh, gee golly, we're multiplying with the same base here, 10 to the second times 10 to the eighth. We add our exponents, and we'd end up with our final answer of 3 48/100 times 10 to the 10th power. Give it a box or a circle or some flair. It's your answer. And I said I'd do B with you. Oh no, this isn't written in scientific notation either. That significant figure is too small. So we want to focus on just that value, and we would think it's 4.026 times. Well, remember, this is bigger. This new number we've written is larger, so this is going to be a negative exponent for the power of 10. And to go back here, we'd have to go 1, 2, 3 decimal places over. Remember, we still have that times 10 to the 9th. So our final answer, 4.026 or 26 thousandths times 10 to the 9 plus negative 3 is 6, 10 to the 6th power. Awesome. Okay, you finish C, D, E, F, and we will check in as soon as you're ready. Okay, taking a look, C and E are written in scientific notation. The significant figure is greater than or equal to 1 and less than 10. And our N, our order of magnitude, is an integer, -7 here and 4 there. But D and F is where you needed to apply your new skills. So taking a look at D, just 45.5 is 4.55 times 10 to the first. We still bring down that 10 to the -6. -6 plus 1 is -5. 4.55 times 10 to the -5th. Then when we look at F, we notice, oh no, significant figure is too small. So if we just look at that value, we know that that is 7 42/100 times 10 to the -3rd. And we still have to bring down the other 10 to the -3rd, and -3 plus -3 is -6. So 7.42 times 10 to the -6 is correctly written in Sino. Nice work, mini mathematicians. Okay, so let's take a look at Tiffany and Jen. So Tiff explains to Jen that scientific value 6 times 10 to the negative fifth is larger than the value of 3 times 10 to the negative second because 6 is bigger than 3. But Jen disagrees with Tiff and believes that 3 times 10 to the negative second is actually the greater value. So who is correct here? Who do we think is correct? So Tiffany thinks that 6 times 10 to the negative fifth is bigger. What do we think? Who do we think is correct? Well, here, Jennifer is correct. Jennifer is correct. And we can say that 3 times 10 to the negative second is actually greater than 6 times 10 to the negative fifth. And if we wanted to rewrite them in standard form, you could. This is, oops, I went over one decimal place too much, you guys. This is if you had the 3 and you went 2 decimal places to the left, you just have 1 0 in to the right of the decimal place. This is 3/100 is greater than 1, 2, 3, 4, 5, 6. 6 goes in the 6th place. 1, 2, 3, 4. Oh, you guys, I made the same mistake. Silly me. Because this is a 5, I'm going to the left 5. There's already 1 decimal place counted for, so I only need 4 zeros. I just got 0 happy. 1, 2, 3, 4, and then the 6. Perfect. My apologies. So what we can think about is you need to look at the order of magnitude to know what decimal place the significant figure will belong to. So there's a couple different ways we can explain this, but we know that with decimal places, the further number of decimal places we have to the right of the decimal point, the smaller the actual number is. So when we are moving to the left, the smaller the exponent, the smaller the number. And when we move to the right, the bigger the exponent, the bigger the number. Okay, so what we are going to do is we are going to apply our knowledge here to classify these numbers. And it says some numbers will appear more than once. And the whole idea here is at the end, we're going to want to list them from greatest to least. So let's start with the first number. So 1.68 times 10 to the negative first. We know that that is going to end up being positive, of course, because it starts being positive. So 1.68 times 10 to the negative first. And from there, now that we know it's positive, is it greater than 1? Between 0 and 1? It can't be between 0 and negative 1 because notice those are only negative numbers. So it's either greater than 1 or between 0 and 1. We know this is between 0 and 1. 1.68 times 10 to the negative first. And that's going to help us order these values from greatest to least. So the next number I will help you out with is negative 3.403 times 10 to the negative second. So taking a look at that, because it starts negative, we are only moving decimal right and left, so it's going to end up being negative. So we'll put that down here. Negative 3.403 times 10 to the negative second. And we think, is that between 0 and negative 1, or is it less than negative 1? Because we are going to the left here, we know it's going to be between 0 and negative 1. So negative 3.403 times 10 to the negative second. Okay, so why don't you take a moment and finish sorting the rest of these numbers, and then when you're done, list them from greatest to least. List them from greatest to least, biggest to smallest. Go ahead, pause the video, and we will look at our answers in just a moment. Okay, let's see how we did. So here are our sorted numbers. You can get all of them on my screen. So listing them from greatest to least, you can always pause the video and see it that way too. Biggest number is 3.78 times 10 to the 6th, then 3.39 times 10 to the 1st, 1.68 times 10 to the negative 1st, 1.68 times 10 to the negative 2nd, negative 3.403 times 10 to the negative 2nd, negative 2.11 times 10 to the 1st, negative 4.53 times 10 to the 2nd, and then negative 7.21 times 10 to the 2nd, ordered from greatest to least. Awesome job, mini mathematicians. I hope you enjoyed our little conversations about Sino, and best of luck on your homework.